Welcome to lesson number 5 related to the shear strength of unsaturated soils and its application in geotechnical engineering practice. My name is Dale Fredlund and I am Professor Emeritus at the University of Saskatchewan in Saskatoon, Canada. There are 3 common engineering applications for shear strength, and these are as follows. Number 1, the bearing capacity of a soil, lateral earth pressure theory, and thirdly, the stability of natural and man-made earth slopes. Near ground surface soils above the water table are subjected to negative pore-water pressures or soil suctions. Negative pore-water pressures add strength to the soil. The ground surface is also subjected to varying weather conditions, and as a consequence, the near ground surface pore-water pressures may change over time. The negative pore-water pressures add a type of cohesion to the strength of the soil. The shear strength of an unsaturated soil can be written in a mathematical form and then used to extend formulations for saturated soil mechanics such that it embraces unsaturated soils as well. The shear strength theory for an unsaturated soil can be viewed as an extension of the historic Mohr-Coulomb theory. In 1936, Terzaghi wrote the Mohr-Coulomb shear strength equation in terms of the effective stress variable for a saturated soil. The shear strength equation for an unsaturated soil will simply be an extension of the well-known equation for saturated soils. Let us define the variables associated with the effective stress shear strength equation for a saturated soil. The equation has an intercept designated as the effective cohesion, C prime, and a sloping angle which represents the effective normal stress. The angle is referred to as the effective angle of internal friction and given the symbol phi prime. The equation is plotted on the next slide. There are other shear strength equations that have been written for saturated soils. However, the intent of this lecture is to build on the classic form of the shear strength equation for a saturated soil. Mohr circles can be plotted using the effective principal stresses, and their limiting extent become tangent to the failure envelope for the saturated soil. The shear strength of an unsaturated soil is controlled by 2 independent stress state variables, and a soil property is associated with each of the stress variables. The selected stress variables are, number 1, the net normal stress, designated as sigma minus UA, or the pore air pressure. Number 2, matrix suction, defined as the difference between the pore air and pore water pressures. To start our discussion on the shear strength of an unsaturated soil, let us assume that the soil properties associated with the change in matrix suction can be represented by a constant slope angle, which is given the variable phi superscript b. Since there are 2 independent variables involved, a graphical representation of the equation will take on the form of a 3-dimensional plot. The axis in the third direction shows that the cohesion intercept is now comprised of 2 components, the effective cohesion, C prime, and the cohesion due to matrix suction. The 2 components of cohesion can be added together to represent an unsaturated soil with a designated suction value. The sum of the cohesion values can be referred to as the total cohesion. In this way, an unsaturated soil can simply be viewed as a soil with an increase in cohesion. Consequently, the behavior of an unsaturated soil is greatly simplified by doing this. constants associated with plasticity solutions, such as the bearing capacity of a soil, are still applicable for calculating the effect of soil suction on the analytical outcome. To further clarify the nature of the shear strength envelope for an unsaturated soil, the effect of cohesion due to matrix suction can be reduced from a three-dimensional surface to contours on a two-dimensional plot. This can be done as long as the shear strength surface does not have a warped shape. The purpose of these various plots is to simply assist the geotechnical engineer in realizing that there are limited changes associated with conventional soil mechanic formulations when taking unsaturated soils into consideration. In 1980, Escario presented a series of tests performed on a modified direct shear apparatus, but he was able to independently control the matrix suction in the soil and the normal stress. The result was a series of essentially parallel contours, each one representing a particular constant matrix suction in the soil. The near parallel nature of the constant matrix suction contours indicated that the angle formed between matrix suction and shear strength is essentially a constant value. However, this need not always be the case, particularly when suctions vary over a wide range. Other laboratory test results associated with other research studies have shown that the relationship between shear strength and matrix suction can take on a nonlinear form as suctions pass through the air entry value and the residual suction conditions are reached. A more general and accurate shear strength equation for an unsaturated soil would be the form shown in this slide. Here, the soil property is simply left to be represented by a mathematical function f sub 1. The nonlinearity of the matrix suction shear strength function is obvious from controlled laboratory results such as those published by Gann in 1986. It is interesting to note that under low applied suction conditions, that is less than the air entry value, the slope of the shear strength envelope is essentially the same as that for an effective angle of internal friction phi prime. Deviation from the behavior of a saturated soil commences near the air entry value of the soil, causing the slope to reduce from a value of 25 degrees to about half that value for matrix suctions around 500 kilopascals. Further laboratory testing programs have confirmed that there is a definite relationship between the soil water characteristic curve of a soil and the shear strength response to matrix suction. With this brief review of the background information, let us give consideration to the measurement of the unsaturated shear strength of a soil. The soil in the field can be subjected to a wide range of suction values. It is difficult, however, to measure or monitor matrix suction in the laboratory without using the axis translation technique. This means that a new increased ambient air pressure environment must be created or controlled throughout the test. Then it is necessary to separately measure the pore air and pore water pressures to which the soil is subjected. This is successfully accomplished by installing a high air entry disc into the base pedestal of a triaxial cell or a direct shear apparatus. Essentially, all research programs on unsaturated soil from around the world have been studied using the axis translation technique. I'm referring to shear strength studies. In 1963, Bishop and Blake undertook an interesting experiment in which the laboratory environment was modified. 2 unconfined triaxial tests were performed on a clay soil. One soil specimen was tested at atmospheric air pressure conditions, while the second specimen was subjected to a translation air pressure of 483 kilopascals. The result is the plots show that the shear strength remained the same for both soils. Stated another way, the axis translation technique can be used to test the shear strength of an unsaturated soil. It is an acceptable procedure. There's one major change that needs to be made to a conventional triaxial cell when testing unsaturated soils. A high air entry disc must be placed onto the base pedestal and cemented around the perimeter. In this way, water must flow through the high air entry disc, thereby allowing a separation of the pore air pressure and the pore-water pressures. A coarse but low air entry value can be placed on the top of the soil specimen, thereby allowing for the control of the pore air pressure. It is the elevated pore air pressure that allows the pore-water pressures to remain positive, thereby preventing cavitation of the water in the chamber below the higher air entry disc. An unsaturated test specimen might change in overall volume during the test. The change may also be in terms of water content or degree of saturation. In other words, a change in water content does not correspond to a change in overall volume for when you're testing an unsaturated soil, as it does for a saturated soil specimen. Consequently, it is advantageous to measure overall volume change of the soil specimen as deviator stresses are applied. This slide illustrates the use of a second inner wall chamber with an accurate differential pressure transducer employed. Changes in water pressure relative to the reference point allow overall volume changes to be computed. There are a variety of stress paths that could be followed when testing for the shear strength of an unsaturated soil. The stress paths are similar to the stress paths that have been proposed and used for testing saturated soils. The test procedures can be labeled as follows. Number 1, consolidated drain tests. Number 2, constant water content tests, which is a new test procedure. Number 3, consolidated undrained tests with pore pressure measurements. Number 4, undrained tests. And number 5, unconfined compression tests. Pore air and pore water pressures must be either measured or controlled throughout the test in order to interpret the results in terms of the stress state variables. The stages involved in testing an unsaturated soil are similar to those commonly used when testing saturated soils. The soil specimen must first be allowed to come to equilibrium with a selected set of stress conditions. For example, a particular applied confining pressure, an applied air pressure, and a controlled water pressure. After equalization of the pressures, an axial deviator stress is applied. Failure conditions are defined in accordance with a selected failure criteria. The stress state variables can be computed at all stages during the shear strength test. The control stresses for various stages of a consolidated drain triaxial test are illustrated in this slide. The stress state can be calculated when equilibrium conditions are established and then followed as axial compression is applied. Failure conditions are selected in accordance with the designated failure criteria. The easiest shear strength test to perform in the laboratory is the unconfined compression test. The soil specimen is simply placed on the loading frame and a deviator stress is gradually applied until failure conditions are reached. While the test is easy to perform, the shear strength measured may be highly conservative in the sense that the measured strength is far too low. It is better to place a membrane around the unsaturated soil specimen and subject the specimen to an appropriate confining pressure. A direct shear apparatus can be modified in a manner similar to that described for a triaxial cell. In other words, a high air entry disc is mounted in the base plate of the direct shear box. The entire direct shear box needs to be enclosed in order for the surrounding air pressure to be controlled. The maximum matrix suction that can be applied to the unsaturated soil specimen will be controlled by the air entry value of the higher air entry disk. The primary advantage associated with using a direct shear box is the reduced length of the drainage path, which results in a more rapid equalization of the applied pore pressures. This slide shows triaxial shear strength results from two series of tests performed on Dhanauri clay by Situ in 1978. The two stress paths were used in the triaxial test program and are as follows. Number one, consolidated drain tests, and number two, constant water content tests. The test results confirm that both stress paths produce the same shear strength envelope. At low applied suction values, the soil responded similar to the response that was obtained from a saturated soil. It showed an angle of internal friction of 29 degrees. As the soil specimen became increasingly unsaturated, the effective angle reduced to almost 1/2 of the 29 degrees. One of the difficult aspects related to testing unsaturated soils is the length of time required to run the test. As soon as the soil becomes unsaturated, its coefficient of permeability can decrease by orders of magnitude. This in turn means that the time required to perform a direct shear test will increase by orders of magnitude. The ceramic high air entry disc also has a low permeability, which further impedes the equalization of the pore-water pressures. The impeded analysis of flow through a soil specimen, 12.7 millimeters in thickness, is shown on this slide. The coefficient of consolidation shows how the permeability and the coefficient of volume change of a soil affect the time required to perform a shear strength test on an unsaturated soil. The testing of unsaturated soils is costly and time-consuming. Consequently, estimation procedures have been proposed to obtain an approximation of the shear strength function with respect to matrix suction. Unsaturated shear strength properties take the form of a nonlinear mathematical function with respect to suction. The unsaturated shear strength is closely related to the soil water characteristic curve, or the degree of saturation of the soil. The shear strength function becomes nonlinear as the air entry of the soil is exceeded. proposed estimation procedures for the shear strength function are adequate for most geotechnical engineering applications. The shear strength function is an estimation of the change in strength with respect to matrix suction. This equation was probably the one shown here, was published by Fredlund et al. In 1996. The shear strength function makes use of the soil water characteristic curve to get the soil's information required to define the function. For example, the dimensionless water content is based on the soil water characteristic curve, which can be defined in terms of volumetric water content, gravimetric water content, or degree of saturation. The kappa variable is an empirical fitting parameter related to the plasticity of the soil. The magnitude of the kappa parameter is based on the interpretation of a number of test results published in the research literature. Its magnitude usually ranges from 1 to 3. Another empirical equation was published by Vanapalli et al. In 1996. In this equation, the shear strength is scaled according to the water content or the degree of saturation, starting at the saturation condition and ending at residual water content conditions. The reduction in the normalized water content is used to reduce the effective shear strength of the soil. The assumption is also made that there is no further change in shear strength once residual conditions are reached. Deformation or ground movement problems fall into two broad categories, depending on the stress level involved. When deviator stresses are low, the problem is assumed to be in the elastic stress range. When deviator stresses are high, relatively high, the problems are assumed to be in the plastic range. There are three common shear strength analyses that are referred to as plastic equilibrium analyses. Namely, first one, lateral earth pressure analyses. Second, bearing capacity analysis. And third, slope stability analyses. Let us consider how active and passive earth pressures are influenced by matrix suction in the soil. The effect of matrix suction can be visualized by comparing the Mohr circles for a saturated soil with those for a soil with suction. The comparison is made for a particular selected vertical total stress sigma V. A soil with matrix suction behaves as though it is a soil with an increased cohesion intercept. It can be seen that the soil with matrix suction experiences a reduction in the active earth pressure in comparison to a saturated soil. Likewise, the soil with matrix suction experiences an increase in passive earth pressure when compared to saturated conditions. It is safe to conclude that suction in the soil will decrease the active earth pressure, and will increase the passive earth pressure. In general, this works to the engineer's advantage for most geotechnical design problems. The distribution of active earth pressure can be calculated using the classic earth pressure equations that are applicable for dry soils, saturated soils. They also apply for unsaturated soils. The only difference in each case is the magnitude of the matrix suction in the soil. The saturated soil is designated as a dashed line. The uppermost portion of the pressure distribution shown in white here indicates the portion where there is no contact between the soil and the wall. The figure also shows that the non-contact portion of the soil against the wall increases as matrix suction in the soil increases. The same comparisons between a saturated soil and an unsaturated soil can be made for the passive earth pressure distribution. In this case, the passive resistance of an anchor would increase as matrix suction increases. The increases in passive resistance are equal to 2 times the matrix suction multiplied by the tangent of the friction angle with respect to suction. The net changes associated with suction can be substantial. Let us illustrate the differences in the active earth pressure against an 8-meter high wall where the soil has various constant matrix suction values. If the soil is saturated with zero suction, the active force would be 200 kilonewtons per meter. On the other hand, if the matrix suction in the soil were constant at 150 kilopascals, there would be no active earth pressure against the wall. The active earth force against the wall for intermediate values of suction are shown as dashed lines. The solid line shows what the active force would be against a 12-meter high wall. In both cases, the effect of suction on the forces against the wall are substantial. The passive earth force, or the resistance of an anchor system, is shown for the case of an 8-meter and a 12-meter wall or an anchor. The soil is assumed to have constant matrix suctions ranging from 0 to 300 kilopascals. No new theory or analytical equations are required to calculate the active and passive earth forces when matrix suctions are taken into consideration. In other words, historic earth pressure theories were calculated for a material with a cohesion intercept and a friction angle. Unsaturated soils behavior is assumed to simply be that of a soil with an increased cohesion, and that cohesion is quantified in accordance with the shear strength equation for an unsaturated soil. The bearing capacity of an unsaturated soil can be viewed as an extension of the classic bearing capacity theories for dry and saturated soils. The required change in thinking is that now cohesion has two components, namely effective cohesion and cohesion due to matrix suction. Prandtl's bearing capacity equation and Terzaghi's bearing capacity theory apply equally well for unsaturated soils as they do for saturated and dry soils. The ultimate bearing capacity equation is shown in this slide. The bearing capacity of a soil is viewed as having three contributing terms. The first term takes the weight of the soil into consideration, and it has a dimensionless coefficient which is related to the angle of internal friction of the soil. The second term takes cohesion into consideration, and it likewise has a coefficient related to the angle of internal friction. The third term takes the effect of surcharge load into consideration. It is the cohesion term that is significantly influenced by the matrix suction of the soil. The various bearing capacity coefficients are only dependent on the friction angle for that of a saturated soil. In other words, the bearing capacity factors are not influenced by suction in the soil. The Terzaghi coefficient of bearing capacity are plotted versus the friction angle of the soil on this graph. The cohesion coefficient is equal to 5.7 for purely cohesive soil. That is, a friction angle is taken to be 0. The dashed lines correspond to the usage of 2/3 of the cohesion and 2/3 of the angle of internal friction. The ultimate bearing capacity of a soil increases linearly with respect to matrix suction in the field. For the assumed soil properties listed in this graph, along with 0 matrix suction, the bearing capacity is 200 kilopascals. If the soil had a matrix suction of 100 kilopascals, the bearing capacity increases to about 700 kilopascals. And if the matrix suction is increased to 200 kilopascals, the bearing capacity increases to almost 1200 kilopascals. These calculations show that the bearing capacity of a soil increases substantially with the cohesion in the soil. The stability of Earth's slopes is commonly analyzed using one of several limit equilibrium methods of slices. The assumptions associated with the limit equilibrium methods of slices for saturated soils can be extended to embrace the unsaturated portion of the slope. Negative pore-water pressures in the zone above the water table have often been set to 0 for ease of analysis, with the perception that the engineer is simply being conservative. However, it is important to be able to quantify the significance of the negative pore-water pressures on the calculated factor of safety. It should also be noted that the trigger mechanism for instability is often located in the zone above the water table, and for this reason, it is important to be able to quantify changes in the factor of safety as suctions change. A sliding mass of soil can be divided into a series of vertical slices, with each slice considered as a free body diagram. All the forces on each slice are the same, whether the soil is saturated or unsaturated. Only the shear force mobilized, S sub m, needs to be defined in a slightly different manner to accommodate unsaturated shear strength. The shear force mobilized needs to be defined using the shear strength equation for an unsaturated soil. A linear form for the unsaturated soil is shown at the bottom of this slide. There is essentially no difference between the manner in which the factor of safety equations are derived for a saturated soil and an unsaturated soil. The normal force at the base of a slice is calculated by summing forces in the vertical direction and solving for the normal force. The shear force mobilized contains the failure criteria and constitutes the only difference between how a saturated and unsaturated soil is analyzed. It is possible to derive a moment equilibrium factor of safety and a horizontal force equilibrium factor of safety equation. These equations take the same form for an unsaturated soil as for a saturated soil. This means that it is possible to solve two factor of safety equations for the slope. The differences in the two factors of safety equation occur because of the way in which the interslice force function is handled in the analysis. Morgenstern in 1965 found that the interslice force function could be adjusted such that the moment and force equilibrium factors of safety would become equal. In order for this to happen, he introduced an empirical lambda factor, which could be visualized as the percentage of the interslice force function that was used in the analysis. The lambda value affected the computed normal force on the base of each slice. By plotting the moment and force equilibrium factors of safety versus the lambda value, it is possible to observe that under a unique set of interslice shear forces, the two factor of safety equations gave a single value. In other words, it is the interslice shear forces where both factor of safety results give the same value. The plot shown is of for a circular slip surface, and it shows that the moment factor of safety equation is less sensitive to changes in the interslice force function than is the force equilibrium factor of safety. A natural question to ask when studying the effect of matrix suction on the stability of a slope is, how much does suction affect the computed factor of safety of the slope? To respond to this question, it is possible to convert matrix suction to an equivalent cohesion value and observe how the factor of safety changes. The graph shown is for a soil with a phi b value of 20 degrees. The analysis is done for a 2-to-1 slope and a 3-to-1 slope. The plot shows that less than 1 atmosphere of matrix suction can increase the factor of safety by more than 50%. In other words, even a small amount of matrix suction has a significant influence on the calculated factor of safety. In the early 1980s, a line shaft was excavated to 25 meters in Hong Kong. Measurements were made of matrix suctions throughout the unsaturated soil profile for more than a year. It was observed for matrix suctions reduced. It was observed that matrix suctions reduced near the ground surface during the rainy season of the year. Also, the water table fluctuated by several meters. However, the rest of the suction profile remained quite constant, with suctions around 80 kilopascals. These observations help geotechnical engineers understand why most of the slopes in residual soils remain stable throughout the year in Hong Kong. It is possible to numerically model changes in the factor of safety of a slope by first modeling seepage from rainfall on the slope. The slope shown here is typical of those encountered in Hong Kong. The water table is at considerable depth, and the zone above the phreatic line is unsaturated. Reasonable seepage boundary conditions were applied to the slope when the analysis was performed. Since the analysis is transient in nature, it is necessary to establish a starting or an initial pore water pressure profile. This was done by first subjecting the ground surface to an average annual precipitation. The resulting pore water pressure profile is shown for the XX cross-section near the midpoint of the slope. The slope was then subjected to a heavy rainfall. At various elapsed times, the pore water pressures were plotted along the XX axis, or XX cross-section. It can be observed that a wetting front did pass downward through the slope. The red line corresponds to an elapsed time of 480 minutes of rainfall. At 480 minutes, the rainfall was assumed to stop. However, there continued to be changes in the pore water pressures in the slope over time. The position of the groundwater table and the pore water pressure contours are shown throughout the cross-section of the slope for an elapsed time of 180 minutes. It can be observed that a perched water table had started to form at the ground, near the ground surface. And finally, after 180 minutes, the perched water table had joined up with the lower water table. The computed pore water pressures were imported into a limit equilibrium slope stability analysis, and changes in the computed factor of safety were observed. The various lines on this graph correspond to the ratio of the phi b for the unsaturated soil, angle of friction relative to the effective angle of internal friction, phi prime. Let us simply focus on the 50% line, where the ratio of the friction angles was 0.5. The results show that the factor of safety starts from an initial value of 1.13 and then falls to slightly less than 1.0 by the time the rainfall stops at 480 minutes. Once the rainfall stops, the regain in factor of safety is slow, but it gradually returns to a value greater than 1.0. This example illustrates the simulation of how an unsaturated seepage analysis can be combined with a slope stability analysis to assist the geotechnical engineer in understanding how the magnitude of rainfall and the duration of rainfall affects the stability of a slope. This lecture on the shear strength of an unsaturated soil has attempted to make the geotechnical engineer aware of the fact that the effect of matrix suction can be quantified for problems related to lateral earth pressure, number 2, problems related to bearing capacity, and number 3, problems related to slope stability. As a result, there are situations where the concept of shear strength can provide value-added benefits in engineering designs. The next and last lecture on unsaturated soil mechanics will discuss geotechnical problems related to volume change, mainly the swelling soils and shrinking soils. Thank you.